Hello all, welcome to the AI driven perception learning and mappings for drones course. This is the lecture on attention layers and transformers. Now in the previous lectures we have studied about memory network neuron, which is the MNN. We saw how it retains the memory across different network neurons. In the last lecture we saw RNNs and LSTMs, right? We saw how RNN, the structure how the structure of RNN is presented to learn the temporal data properly, and in this lecture also we will do a quick recap of the RNN and LSTM structure. This is to understand that how does attention differ exactly compared to the RNN and LSTM structures, how it is more efficient, and building up upon attention layers we will focus on self attention, multi-head attention, and we will also quickly review the transformer architecture, which has an encoder decoder, and encoders and decoder both have attention heads as well as the feed forward network, right. Now we have reviewed the sequential learning problems where we saw this particular example of task completion. We observed that the inputs and the outputs are not of always the same length, so they have a variable temporal context. However, for each of these tasks, for each of these inputs and outputs, the task essentially remains the same. So this could be about a text completion that we see here, where we are supposed to give an input which is an incomplete input, and the model is supposed to complete the whole word, right, and depending upon the input it would approximate an output. However, since we keep on adding more letters, the context of the input keeps changing, and hence corresponding to that even the output context keeps changing. This could also be across videos. So we saw an example of many to one or many to many, where we feed a video, and based on these video it can either assign a single label, which is the description, which is the action itself, or it can give a description of the action, which would be a many to many case, right. Now our goal throughout this particular module is to focus on models which can learn sequentially, which is learn from learn from the time series data, right. Now we also had a brief discussion about feed forward neural networks, where essentially the input is at a particular time step t and the output is at a particular timestamp t, right, and there is a forward pass and we calculate the error and then we update the weights. However, in this whole model or whole training, the previous states or even the future states are never taken into account, right. Compared to that, we have observed the feedback neural networks, and in this case a recurrent neural network, where the dependency is on the current state, which is xt, right, and the output yt then also depends upon the previous states, which is xt minus 1 and yt minus 1, right, and hence the sequential relationship is focused more, not just matching from the current input, right. Now we have discussed about RNNs, and we saw that RNN have this particular structure where there is an input, in our nomenclature it is xt, and we have a corresponding output. There is a context or a memory state which could be represented as the hidden state, right, and the hidden state works or depends upon the previous input as well, right. Now we did see certain advanced RNN architectures as well. However, the important part is for the sequential learning task, the memory is focused or retained in this particular context, right. We also saw the LSTM architecture, which is essentially there are repeating modules, and the LSTM module would have one cell and 3 gates, which is the forget gate, input gate and the other gate, and the focus is to retain this information from the cell state from the t minus 1th state to the ctth state, right, and this is how the information could either be retained or it could be forgotten, right. Now we also discussed about the vanishing gradient problem in RNNs, right? RNNs are very good while for understanding the temporal nature of the input. So, for any time series information which could be video or any other sort of data, RNNs are effective in learning the structure. However, as we discussed even in the last lecture, the influence of the inputs or the hidden states of, let us say, x0, x1 and x2 would be very less on ht, which is the tth state, right. And this is because the relationship to all of these takes a very long structure, right, and this is essentially a structural limitation, right. But we observe that the influence of the previous or the inputs at a very start of this, which is x0, x1, x2 would have less influence. Now, this is a problem with long term dependencies for both RNN and even for LSTMs, right. Now, one intuition could be that when we have this sort of an architecture and we have hidden states which we can observe here, one way could be, instead of passing through the whole path which is from each state, there could be a way to understand or retain the context of all the states, right. So, instead of passing through the network, we could have a direct connection with the outputs as well, right. Now, this is the fundamental intuition that is used for the attention layers, which is to use the context in such a way that you are attending to each of the timestamps or each of the time series data without using this long form structure, directly connecting it with the timestamp, right. Now, the intuition about attention is that attention vectors essentially correlate all the elements in the input. They put a weight on each of these elements and then based on the task it assigns the priority, right. So, for example, let us say that we have a photo of Shibu. Now, if we want to identify Shibu, we know that there are certain features which are very important, and we can observe that there are certain features which are not that important to identify the class of Shibu, right. And with that, we also know that there is a correlation between these features that we observe, right, and the correlation with the other features is not that much, right. So, the distinguishable features of Shibu would have a high correlation between them, and features which are essentially redundant would not have a very meaningful impact or meaningful context with respect to different features for Shibu, right. Now, this could also be understood in a different task. So, let us say that we have this sentence which is she is eating a green apple, right. Now, the verb eating would have a high correlation with apple, but not with the word green, right. Now, attention is a way where when we highlight a particular word, we can understand its priority for all the words in this particular sentence, right. Now, when we correlate eating with eating, it is essentially a self attention that we are focusing more on the word itself. But if we focus on other words, we can understand that based on the question or based on the context, some words would have a higher priority, right, and some words would not have a very high priority. So, this is essentially how the attention mechanism or the attention vector works, which is it focuses on the context for the task. Based on the context, it assigns weight for each of these inputs, and based on these inputs, it essentially has a meaningful output, right. Now, the goal of attention is to create shortcuts between the context vector and the input source, right. So, let us take this particular example. We can see that this is the input or the source. We also observe that it has a specific hidden layer. We can identify H as H1, H2, right, or just so it is essentially taking both the hidden states, right. Once we have a hidden state, we have a zone where we have defined context vector, right. Context vector C depends upon these alignment weights. The job of alignment weights is to align the input and the output. The way it aligns is focusing on the hidden states of the input and output, right. Now, this is very intuitive in the sense that if we focus on the particular timestamp or the output yt, which is a hidden state st, right, we observe that it actually looks over or has inputs from all the previous timestamps directly, right. So, it is not propagating in a okay. So, for RNNs we had observed a structure like this, right, and we observed that for y to have any information from x0, it has to traverse through this path, and when this path is very long, which is essentially throughout a lot of states, there would not be a meaningful interaction between x0 and yt. However, if we observe this particular mechanism where we can see that there is a specific hidden state for input, there is a specific hidden state for the output, we observe that the hidden state st depends upon all the previous states, right. The alignment weights is essentially trying to weigh which of the timestamps or which of the inputs or hidden layers are more important, which is why which would be reflected in alpha, and using this we generate a context vector which we define as C. Now, the context vector essentially learns the context of each of these input corresponding to the output at any timestamp, in this case yt, right. Now, the context vector has access to the entire input sequence, as we can observe here, right. Once it has this particular once it takes this input sequence, the goal is to align the source or the input with the corresponding target or the output, and the way this is done is using the hidden states of both, right. Now, context vector relates both the encoder, the decoder, and focuses on aligning the source and target, right. Now, let us say that we have an input which is the source, we have output which is the target. Now, the decoder network has the hidden state, which is the hidden state of the output layer, right. It is defined as st, which is a function of the previous hidden state of the output as itself, the previous state of the output, and the context vector, right. Now, context vector is the part that links both the input and the output. Now, context vector can be defined as a weighted sum of all the hidden states of the input, which is hi, with a learnable alpha, right. Now, alpha may be learnable or it may not be learnable depending upon how alpha is computed, and we will look at how alpha can be computed in various types. Alpha focuses on aligning the input and output, which is y and x. The way it does is by relating the hidden state of both y and x, right. So, it essentially generates a score for st-1 or hi, right. Score is we are trying to compute the similarity between these two states, or we are trying to generate a score to see which of the states is more helpful for generating the best output prediction, right. Now, once we have alpha, we can essentially generate the context, and once we have the context, we can modify the hidden states, right. Now, if we observe this particular structure, we do observe that the attention is to create shortcuts between the context vector and the entire input states. We can observe that the equation which is ST can be generated taking the previous input, the previous output and the context. We can see that the context vector CT is essentially a weighted sum which can be observed here. So, we have hidden states, and for each of these hidden states we have a dedicated alpha, right. And finally, the way we generate alpha could be a learnable way, or it could just be to generate a score or to relate which of the hidden states of the output is closer or meaningful to which of the hidden states of the input, right. Now, there are various ways where we can calculate the score, or essentially we can generate alpha, right. It could be in a content based attention, which is essentially just taking the cosine similarity between S and H, right. It could also be in this particular format, which is additive, which generates or defines the score given here, where W and V may be learnable weights, right. So, we could just compare, or we could compare using certain learnable parameters as well, right. And throughout the duration of training, these learnable parameters would keep on updating, right. It could also be based on a very general form, right, which is S transpose WA, where W is a trainable weight. Now, these last, which is the dot product and scale dot product, are of our importance because this is something which is used throughout, right. Now, dot product is a very simple operation where we have two vectors, right, and we are trying to understand which is similar, which is not similar, right. Now, essentially it is used because it is very simple, in the sense there is no learnable weight, there is not much complexity. And finally, we have the scale dot product, which is just the dot product divided by root of n. Root of n is added for stability constraints, right. So, let us say if this particular dot product is very close to 0, it does not give us any meaningful information, right. So, okay. Okay. Now, since we have gone over the attention mechanism, which is trying to relate the context vector to the input and output, let us focus on the transformer architecture as well, right. Now, the task that we will focus on is to take an input which is in French, right, and convert it into the output which is in English, right. Now, this is essentially an NLP task, which is language translation. However, our goal is to focus more on the transformer architecture and define what are the architectures used, which is self attention, multi head attention, feed forward networks, etc., right. Now, when we have a dedicated input and a dedicated transformer layer, as even observed in the segmentation tasks, we have a corresponding encoder and decoder layer, right, and the functionality of both of them are quite similar. We have an input which is in French, it passes through the encoder to generate a compressed information, which is then passed to the decoder, and then we generate the output which is in English, right. Now, if we focus on this particular architecture more, we observe that the encoder and decoder can be broken into n states, right, and this is so the encoders and decoders could be broken into n states. Here it is, the number is 6, right. Now, all of these encoders have very similar architecture, right, and which is why we will focus only on one of these encoders, because once we understand the functionality of one encoder, essentially all of them are just repeating, right. So, again let us focus on this particular architecture. Now, if we observe, again we have an input which corresponds to a particular encoder. The encoder then generates a compressed version and processes it through the decoder and then outputs the actual value, right, and this would essentially be trained in an end to end manner. So, so the model would generate an output, calculate the loss E or calculate the loss capital E, right, and again to minimize the loss it would keep updating the parameters. Now, if we focus more on this particular part, which is the input and the corresponding encoder, which is the first layer, right. We observe that there is a corresponding input highlighted here. From this input essentially we generate an embedding, which is a word embedding, right. Now how do we generate a word embedding? We have a word which may be passed through a particular or a very generic word to vec kind of a encoder, and once we have this we project it into a feature space, right. So word to vec is a very common way to project words into corresponding features, right. Once we have these features we pass it through the self attention block. Once we pass it through the self attention block, each input has a corresponding embedding. These embeddings are then passed into the feed forward neural network, which is essentially a fully connected layer. This is something that we have been discussing since the first lecture. Finally, the output of encoder 1 can be highlighted as R1, and as observed this is again fed into the next encoder, right, and this goes on in this particular case for 6 times, right. Now let us understand attention at a very high level. So let us understand self attention at a very high level. Now let us say that we have a particular sentence which is the animal don't cross the street because it was too tired, didn't cross the street because it was too tired, right. Now let us take this particular word, right. Now this is something that we even did in the previous slide. So we have a particular sentence, and if we select a word which is it, we want to understand the importance of this particular word to all the other words in the sentence, right, and this particular figure is trying to do exactly that. So we did it, or we can do it using alpha, because we know that the better the alpha the more weight that particular input would get, and that would directly influence the context vector C, right. Now if we observe the input here, if we take it, we do understand that the focus is more towards the animal. So the model is able to understand intuitively that it refers to the animal, or else it could be the street, or it could be 2, right. But there are a lot of words where this attention is not focused at, right. Now this is what essentially the self attention is trying to do, which is with respect to a particular part in the input, what is its important throughout the whole input, right. So what is the influence of the word it throughout the whole input or the input sentence, right. Now this is just a high level understanding. Let us go into how it actually works, right. Now the first step is when we have an input which is say thinking machines, right. Now for this particular example, thinking machines is the input that we give to the model, right. So it is not just we étudier, it is thinking machines. Now when we have input, we generate an embedding, and this could be through something known as word to vec embedding, and there could be other ways also to generate embeddings, right. This is just one very vanilla way to generate these embeddings. Once we have these embeddings, we have query keys and values, right. So we have weight vectors or weights for each of these query key values. Now what essentially is done is we would multiply x1 dot wq and we would get q1. Similarly, we would multiply x2 into wq and we would get q2, right. And similarly it is for all the rest of the vectors we see here, right. So when we multiply the weights which is query q value, we generate these vectors which is again q1, k1, v1, which are the vectors we get after the multiplication. So the first step is to calculate these vectors from the encoder's input. Once we have that, we calculate an self attention score, right. So we have embeddings q1, now we have k1, q1 and v1. What we try to do is generate a score which is essentially multiplying q1 with k1 and q1 with k2. So again this is to understand the influence of the word thinking in the sentence thinking machines, right, which is why we multiply q1 with both the keys, right. So q1 with both the keys. Now the next step is to divide it by the number square root of 8, which is essentially just the dimension of the keys. Once we do that, we apply the softmax to convert this into a normalized version. Lastly, once we have the score which we obtained from normalizing or generating the softmax of q and k, which is query and key, finally we multiply this with the respective values as well. So we multiply it with V1 and V2, right. So the softmax for each of the inputs are again multiplied with their respective values, and we generate embeddings Z1 and Z2, right. Now to summarize what we are trying to do is we multiply the query and key, we divide it by the dimensionality of key, we take its corresponding softmax, and once we generate this softmax we multiply it with the value. This generates the embedding Z, right. So when we have an input and we pass it through a self attention block, this is essentially generating the output Z, right. Now let us look at the multi-head attention. In the previous case we only had one query key value layer, right, that is why it was self. Now in this particular example, when you have multiple attention heads, which is attention head 0 and attention head 1, the goal is that this gives it more representation subspaces. Okay. It gives the attention layer more representation subspaces, which is essentially parallel subspaces where it can explore and learn better, right. So in the first attention head we have a corresponding weight for all KQV. Similarly for the first attention head, which is head 1, we also have corresponding KQV, right. Now this process for this particular example could be across 8 attention heads, right. So we have an input, we generate an embedding, and we follow the same procedure across what we saw in the self attention block, which is softmax of qk by under root dk times the value, right. This is for 1. Now for each of these heads we would generate this output of Z from Z0 to Z7, right. This is again essentially we have multiple subspaces available to us, which is why it could learn better with more learnable parameters, right. Now once we have multiple heads, when we have all these heads, now the problem is if we have multiple heads it still needs to be compatible with the feed forward network, right, which is why all of these heads could be concatenated. Once we concatenate it, we multiply it with a separate weight W0 so that it comes back to the dimension of Z, which is the required dimension for the feed forward network, right. So this particular step is just to reduce the dimension meaningfully so that it is compatible with the FFN layer, right. Now let us look at the self or the multi-head attention at one go. So we have one particular input. The input could be passed through word2vec to generate the embeddings X. It could be passed through multiple attention layers, we call this as multi-head. We can generate corresponding KQV pairs which could then be passed through each, that could be passed and generate the embeddings Z, which is from Z0 to Z7 since there are 8 attention heads, right. And finally concatenate all of them multiplied with the weights to generate the final embedding Z, right. Now this whole procedure could just be summarized as passing it through a multi-head attention and generating it as Z, right. So we can in the figure just put a multi-head or a self attention head, but we know how the working is for all the layers, right. Okay. Now multi-head attention at a very high level could be that, let us say in the same sentence, which is the animal didn't cross the street because it was tired, and let us look at the influence of it, right. Now, we can observe that the orange band mentions attention head 1 and the green bands can mention attention head 2, right. Now, again these are just descriptions we do for our better understanding, right. Now, what we observe is that one of the attention heads focuses more on say the animal, right, and more on say the word 2. The attention head which is in green focuses more on the words like street or more on the words like tired, right. So, multiple attention heads have this particular functionality where one head can focus on one type of an information and the other head could focus on the other type of information, right. This is the utility of multi-head attention, but yes, since we added 8 multi-head attention, we now know that the complexity of this would be much more than a single head, right. Now, if we look at attention at a very high level, what we observe is that we have an input which is converted into an embedding. Now, let us look at positional encoding, right. So, when we look at this particular sentence, so this sentence previously was thinking machines, now it is changed to the French sentence which was our original task. Now, for each of these words, we know that each of these words have a specific place in the input or in the sentence, right, which is je suis étudiant. All of these words have a specific order that needs to be maintained, which generates a meaningful sentence. Positional encoding's job is to retain this particular information. Now, what happens is for each input we can add positional embeddings, and the job of positional embeddings is to store the order of each of these inputs in the sentence, right. And this is done, let us say, for a NLP task for sentence. For an image, let us assume that we have an image which is 3 cross 3, right. Now, each of these patches could be broken down, and once it is broken down, it could be passed through the transformer block, right. Now, this ordering of all the patches is something which is retained with the help of positional embedding, right. Now, this could be generated with like it could be learnable, or a particular encoding could be used to understand or retain the order of the inputs, right. Now, let us look at the illustration of transformer focusing more on the encoder decoder, right. So, in the previous slides we just saw the encoder and decoder. This essentially is highlighting the whole structure, right. So, we can see that the input is there, again the input has been changed to thinking machines. We generate an encoding, we add positional embeddings. Once we add positional embeddings, we pass it through the self attention block, right. Now, again this is something that we discussed, just writing the self attention block is now okay for us because we understand the functionality of self attention, right. We understand how KQV pairs are generated, how the operation happens, which is softmax of multiplication of K into Q and then directly with V, right. Now, once we generate the embeddings which is Z, right, once we generate this embeddings, the add and normalize layer essentially takes the input X, adds it with the output embeddings Z, passes it through a normalization layer, and then it is passed on to the feed forward network, right. Now, this essentially is the structure of encoder 1, right. Now, we can observe from here there is one encoder, but there are in the whole structure 6 of these encoder layers, right. So, again we only focus on one structure, but we know it is a recurring fashion of 6 encoder layers, right. And one more thing here is, this is a self attention block, right, which is why when we add X plus Z, we know that the dimension of X and Z should be maintained, right. Now, if we add a multi-head attention here instead of self attention, right, we would have Z1 to Z7. Now the operation that we saw earlier, which is to convert Z1 to Z7 directly to Z, which is passing through a weight WQ. This is the reason why it is used, so that we can maintain the dimension, right. Okay. Now coming back to the encoder decoder structure, once it is passed through the encoder, we also observe a similar structure in the decoder as well, right. So we have an encoder, we have a decoder, finally the output of this is a linear layer, which is then passed through a softmax layer to generate the probability distribution, right. So this is how the transformer architecture works, right. It is slightly different compared to the CNN architecture we saw, where we have an image and it is passed through a CNN block and then we have a fully connected layer, right. Here instead of only an encoder, we have both the encoders and decoders, right. Now this is just a quick GIF to understand the working of whatever is going on, and it is highly recommended to read this block, right, because it will make a lot of things clear for you. So we have an input which is a French input, and we want to translate it into the English version or the English translation. We generate embeddings, add the positional embeddings, pass it through the encoder, right. The decoder takes the previous input, which is t minus 1th stage, along with the input from the encoder, finally passes it through the linear and softmax and generates the output, right. Okay. Finally, this is to just quickly review the DETR block. This is something that we observe, or this is something we will discuss in the object detection part in detail. This is just to go over the DETR architecture once, right. So we have an input image which could be I. This input image is fed into a CNN block. In the CNN block we have the positional embedding, right. Positional embedding's job is to retain the order of each of the tokens that are generated, right. Now we pass it through a transformer encoder layer, right, which takes these features and outputs. Then it is fed into the transformer decoder layer along with the object queries. Object queries is something we will discuss in the object detection lecture, right. Now once we have transformer decoder, it essentially feeds into the fully connected layers, which is the FFN block, right. Now again DETR is something we will discuss later on, but this is just to discuss that based on the functionality of positional encoder and based on the brief description of the encoder and decoder used in transformers, which would use multi-head attention and the feed forward network, we do understand the building blocks of DETR. However, how DETR is used for object detection is something we will see later on. Okay. So to summarize this lecture, we focused more on the sequential learning task. We quickly did a review of the RNN and LSTM. We saw how the architecture focuses more on a long term dependency. We also saw the motivation for attention mechanism. We saw how attention mechanism works, where it generates an alignment score between the previous hidden state and between the input hidden state and the output hidden state. We saw how different equations or different similarity scores could be used to generate alpha, right, and from alpha we can generate the context. Context essentially is trying to rank the importance of different timestamps for the current timestamp, right. Thank you.